Dear friends, welcome to the 16th video lecture on differential geometry. I will remind you basic things we have done last time. We defined several things, but the last thing we defined was local isometry. So a map from M to N is a local isometry. If it is smooth, of course, if it is smooth and uh, satisfies this f star u dot f star w is u dot w for all vw in tpm for all p in m. So if f is a smooth map that preserves the inner product, then we call it a local isometry. Of course, if it is a local isometry, then f star is a isomorphism because it's a map from a surface to another surface, so it's an isomorphism. It's injective. F star is injective. Therefore, by the inverse function theorem, F is a local diffeomorphism. We have seen those last time, so I won't write it again. We also proved the following fact. Uh, uh, let F be a smooth isometry. No, smooth mapping. Sorry, smooth mapping for each surface patch surface surface patch X from D to M. Consider the composite surface patch. No, composite map. It doesn't have to be a surface patch. X bar, which is defined from, which is just defined as F composition X. So it is from D to N. Then the conclusion is this. Then F is a local isometry if and only if uh, for each uh, surface patch X we have E equals E bar, F equals F bar, and G equals G bar. Okay, we proved this last time. Now, today I promise to give some examples. Let me do that. Okay, first example is this. Let M be the cylinder given by this equation, and X a smooth mapping. It's a parametrization. Metrization given by X of UV is r times cosine u over r times sine u over r, and v. We have computed before, uh, we have uh, computed before that for this surface patch, E was 1, F was 0, and G was 1. And we know that these values are also the values for the surface R2, right? Hence, uh, X is a local isometry. Hence, X is a local isometry. Since for the uh, xy plane, E is equal to 1, F equals 0, and G equals also 1. Also, okay. Well, this is not a surprise actually. This map is a local isometry. It is because of the following. You see, this is the plane, and I just bend it like this without distorting, uh, you know, stretching or contracting it. I just fold it and obtain a cylinder, and then you can open it up again. You obtain the plane back. That's why we don't actually, change the shape of it. We apply some transformation, but that doesn't disturb the local geometry. For example, if you are a little insect on this, very tiny insect, you don't realize whether it is a cylinder or a piece of plane. Okay, uh, so this is reflected, in differential geometry also by these terms. Okay, another example. Local isometry uh, from a helicoid onto a catenoid. Okay, so let's see what this is. Let XUV be the following parameterization, actually surface patch, U times cosine V sine nu and nu, be a patch for the helicoid, and YUV given by this GU HU cosine nu and HU sine nu. Uh, well, so, okay, I use V, so this is V, okay, where GU is this function, it is just sine hyperbolic HU inverse sine hyperbolic U, and HU is this function 1 plus U squared, and this is the parameterization, be a parameterization. for the catenate. Okay, so let me draw these figures, I mean these surfaces. Let me try to draw them. Okay, this is the helicoid, and this is the catenoid. So here is, okay, like this. Okay, and here is the map between them. So this is the helicoid and catenoid. Helicoid and catenoid. And there is this map between them, F, given by, so okay, F of x uv. If you choose a point here, let's say with uv coordinates, then the image of this is just y uv, is an isometry. One can check this with E and E bar. So E, F, G are for the helicoid, and so here I have E, F, and G, and here I have E bar, F bar, and G bar. These are both 1. F and F bar are 0, and G and G bar are given by 1 plus U squared, which is H squared UV. And what happens is that, this map just wraps this helicoid around this surface. Okay, so this red arrows becomes this red uh, arrows like this. Okay, and it's an isometry. Okay, and finally I have another definition. I will finish with this definition. A mapping F from M to N of surfaces is conformal, is called conformal if there is a smooth real valued function lambda from M to 0 infinite, so that uh, norm of any vector under the derivative of f is just lambda p times this for all vp in tpm and for all p in m. So what this is the following: f star preserves distances up to a multiple at each point. But the thing is that if you are at a point, then this constant doesn't change with respect to the vector. It is the same constant for all vectors at that tangent space. Conformal maps is known that they don't preserve distance, as it is clear from the definition, but they preserve angles between them, between vectors. Uh, and they are very important class of maps. Actually, complex analytic maps of the complex plane are conformal maps. Okay, if they're at the point where the derivatives are not zero. All right. Now I'll start a new section. 6.5. We will make use of the stuff we have seen here. Intrinsic geometry of surfaces in R3. What we mean by intrinsic, it means we mean geometrical properties of the surface, but not of the ambient space that contains the surface. Okay, the properties which are kind of independent of the embedding of the surface into R3. Okay. Okay. Like intrinsic distance we have seen at the beginning of the last section. The first result of this section is the following. The connection form W12, which is minus W21, is the only one form on the surface that satisfies the first structural equations. What are they? They were d theta 1 is omega 1 to theta 2, and d theta 2 is omega 2 1, so minus omega 1 2, which omega 1. Okay, let's see the proof. Okay, now let's compute d theta 1 and d theta 2 on two vectors in the frame. So let E1, E2 be a frame on the surface, a local frame. Then what is d theta 1 of E1, E2? Well, this is, well, since d theta 1 is this, I get omega 1 to E1, theta 2 E2, minus omega 1 to E2 and theta 2 E1. However, we know that since omegas are the dual forms, this is equal to 1 and this is equal to 0. So the result is then This is just omega 1 2 of E1. And similarly, d omega 2 E1 E2. So if I do that, I will get what? Minus omega 2 1 E2. Okay. Let's see. E1 E2 minus E2 E1. So this is just, of course, 1 2 E2. So we obtain this. So omega 1 2 E1. So this one form on the vector E1 is equal to d theta 1 E1 E2 and d theta 2 E1 E2. Wait a minute, I made a mistake. Okay, so d theta 2 is, so if I put E1 E2, E1 on this vector, E2 on this vector is 0, which is 0. And then E2 on this one minus, and then E1 on this one. So I get this. Okay. Let me check. Okay, I did correctly. My notes were not correct. Okay, so this means what? Omega 1 2 is determined by these values, okay, provided that it satisfies this equation. So whenever a one form satisfies this equation, then omega 1 2 is given by theta 1 and theta 2 in this form. Therefore, this proves the lemma, because if we had any other one form satisfying the same structural equation, then they were given by this formula again. Therefore, it is equal to this form, because two one forms are equal to each other if they agree on basis vectors. And here we see that the values of the one form, connection one form, on the basis vectors are given like this. Okay, so they determine the one form uniquely. Okay, we have another lemma. Let me state it here. Let f be an isometry, and let E1, E2 be a tangent frame on M. If E1 bar, E2 bar is the transferred frame field on M bar, then we have the following conclusions. First, theta 1 is just F pullback of theta 1 bar, theta 2 F pullback of theta 2 bar, and the second part, omega 1 2 is just pullback of omega 1 2 bar by F. Here, of course, by the transferred field, we mean this. F1 bar is just F star E1, and E2 bar is F star of E2. So you transfer this frame by the isometry, and you compute the dual forms and connection form with respect to this transferred frame. You obtain new connection form and one forms, and when you pull back those forms by F star, you get back to the dual forms and connection forms on M. This is, of course, something, straightforward. Let's see the details of the proof. Well, F star of theta I on the vector EJ, theta RI bar. Well, what is this? This is by definition theta I bar of F star of EJ, but this is just theta I bar of EJ bar. However, this is just Kronecker delta IJ because these are dual objects. But you see, this is also equal to theta I at EJ. So what I see is that this one form and this one form. So let me, okay. So this one form and this one form agree on each basis element. So this is true for all I and j, but in particular for a fixed I, it holds for all j. This means this one form and this one form are the same. Hence, theta I is equal to F star of theta I bar. Okay, for all I. Okay, so this proves the first assertion. For the second one, okay, for the second one, consider this. Well, by the previous lemma, which characterizes connection one forms, by the previous lemma, it is enough to show that okay. uh, d theta 1 bar, d theta 2 bar, uh, d theta 1 and d theta 2 satisfy the no, it is enough to prove the following. Omega 1 2 and f star omega 1 2 bar satisfy the same structural equations. Okay, so all right. Since we have d theta 1 bar, which is this, right? We know this because theta 1 uh, and omega 1 2 are the dual form and the connection 1 forms for the transferred frame field. We have this, and we have similarly this from the structural equation for the surface m bar. We get by using pullback what f star d theta 1 bar f star omega 1 2 bar wedge omega 2 bar, and this is equal to f star of omega 1 2 bar wedge f star omega 2 bar, but this is also equal to d of f star of omega 1 bar. However, by part 1 we know that this is just theta 1 and this is just theta 2. Well, similarly, by taking pullback of this via f star, similarly we get this d of theta 2 is f star omega 2 1 sorry bar wedge theta 1. So what we see is that this form f star omega bar 1 2 satisfies the first structural equation, which is satisfied by omega 1 2. But we know that by the previous lemma there's only one such form. Therefore, omega 1 2 is equal to omega 2 1. Hence, by the previous lemma, omega 1 2 is just f star of omega 1 2 bar. And this finishes the proof. All right. Now, finally, we have the most important theorem of this uh, study of surfaces. One of the most important theorems, Gauss's theorema egregium. The important theorem of Gauss. So, what is this? Theorem states the following: Gaussian curvature is an isometric invariant. Explicitly, if f m to m bar is an isometry, then Gaussian curvature at any point of m is equal to the Gaussian curvature of the surface m bar at the image of that point. This is true for all p in m. Okay. Now let's see why this theorem holds proof. We have made a lot of preparation for this. Okay. Let P be a point on the surface and E1, E2 be a local frame, a tangent frame field. At P. Also let EI bar is just F star of EI as usual, I from 1 to 2. By the previous lemma, by the previous lemma, we have this. F star of omega 1 2 bar is omega 1 2. On the other hand, by section 6.2, we had these equations for the Gaussian curvature. On the surface m bar, if we take the derivative of the connection 1 form, omega 1 2 bar, we get minus the Gaussian curvature times the 2 form, which is omega 1 bar times h omega 2 bar. So thus, if I pull back this d of f star omega 1 2 bar, this is just f star of d omega 1 2 bar, but this is just f star of what, minus k bar theta 1 bar which theta 2 bar. Well, here I have a 2 form and a coefficient function in front of it. Its pullback is given by this. You take composition of these two, so this is just k of f minus k bar of f, and then f star of theta 1 bar and f star of theta 2 bar. Alright, so this is minus k bar of f, but we know that this is theta 1 and this is theta 2. Okay, alright, but we know that this is just omega 1 2 because d omega 1 2 because f star omega 1 2 bar is this. However, omega 1 2 bar is equal to what? That's also equal to minus k theta 1 wedge theta 2, and this is equal to minus k bar of f theta 1 wedge theta 2. Well, these are the same two forms which are non-degenerate on the tangent space, and they agree, therefore their coefficients must be the same. So this means K is equal to K bar of F. And this proves the result. Well, why this theorem is important? Because it tells us that, if you have an isometry between two surfaces, at the points, corresponding points, the Gaussian curvature doesn't change. So to change the Gaussian curvature, you should use a map which is not an isometry. In other words, if your transformation preserves inner product, and therefore if it preserves distances, if it preserves the metric, then it preserves Gaussian curvature. This also implies the following, of course. If a smooth map, doesn't preserve Gaussian curvature, then it cannot preserve lengths. It cannot preserve distances. It cannot be an isometry. In particular, we have this famous corollary. Any part of a sphere is not isometric to any part of a plane. Why is that? Well, because for a sphere, curvature is constant and it is positive, and for a plane, curvature is zero at all points. Therefore, there is no isometry which maps a piece of a sphere onto a piece of a plane. This means what? This is, this has very important consequence. What is that? The Earth is a sphere, and if you want to make a map of a piece of a Earth surface, then the map on a plain paper cannot be isometric to the original shape on the sphere. Why is that? Because you cannot keep the distances up to any scale actually. So there is no true map of a sphere of the Earth on a plane, on a paper. So if you draw a map on this plane of some region on the Earth, there is no way it will be a true map. Okay, you have to distort distances in order to plane a piece of sphere on a plane. So that's a very important fact. All right. So let's stop for today. Bye bye.